И теперь перемещаемые элементы. Да, ниже, вот. Теперь это можно, ну, либо так, либо...
Наверное, это
так.
много слишком. Да. Вот, теперь вас тоже видно, Алексей.
Я себя сглушил. Да, ну, добрый день, уважаемые коллеги. Володя, ну вы у нас будете или Антон, кто у нас
Я могу
ведет?
представить докладчика.
Антон изъявил желание.
Да, давайте. А Джунхуй есть?
Да.
Ну, так что все по-английски у нас будет.
Yes. Я, кстати, посмотрел мем с этим. Видно? Это следуется монитором. Завтра мы прикусим, да? И просто про заворках. Все свои. Просто брать. Даже половина. Да. Но я думаю, что оно такое, может быть, туда, но там есть некий старенский. Я думаю, что возможно будет. Мне кажется, это частично был первым. Ну, условно, ну, не то, что условно, но просто хотел бы при этом выбрать, но просто так логично будет. Дождем. Если нам надо сказать, кстати, Саша. Чтобы мышка все полилась в эту сторону, что-то. Все, есть.
All right. Dear colleagues, it is my great pleasure to introduce our new member of our team, Iurii Tikhonov, who has just arrived from Normandy, as I understand. He did his PhD at Université Picardie Jules Verne, named after Jules Verne. And now he was a part of a big European network related to Ferroelectrics, as I understand. So now he will hopefully bring this knowledge and this this network to our team at the Precursor Center. So please, you have approximately 1 hour and
Okay, thank you. Thank you very much for the introduction. Thank you much for invitation. The name is a little bit overcomplicated. Basically, I want to share with you results, my PhD thesis, and I want to share both theoretical, experimental aspects, some applications. So let's go. First of all, during this work, we studied ferroelectric materials. Maybe it's not the most popular material in the world as compared to semiconductors, for example. They belong to a very wide class of dielectrics, and if we need to characterize ferroelectric materials, then it's best characterized by, first of all, spontaneous polarization that persists even without applied electrical fields. And also, ferroelectric materials have some memory effects which result in hysteresis loop. make little historical introduction, I want to share some lesser known facts, but pretty entertaining facts. So, ferroelectric materials started in the middle of 17th century in the place called La Rochelle. Gian Signetti and Elis Signetti, father and son, they had like family business, family pharmaceutical business, and they synthesized what we call now Rochelle salt. Here you can see a usual formula of this material. As you may guess, as a business was about pharmaceuticals, and at this time, it's not somehow related to electronics and even to physics. So what they actually did, they synthesized a mild drug, namely laxative. And it was so good that even 300 years ago, you can see here, it's a box of this drug that was sold in United States.
What is it used for, this drug?
I thought it's laxative.
No, as you.
Yes. I don't know the whole story, so maybe they experimented on themselves. So this is hidden from us, unfortunately. Okay. And from this time, I can tell a lot of names like Curie, Debye, Langevin, even, Schrödinger, who actually coined the term ferroelectrics. But the most interesting person for us, I think, is Thomas Edison. Here's a photo of him with some interesting device. It's called phonograph. And basically, it's the first real application of Rochelle salt. So this device was used to record sounds and produce them. Scientific American this year wrote an article about this invention, and author wrote very interesting thing. Speech has become immortal. It was so nice invention, but it was too expensive and sound was too horrible, so it didn't become popular. But what I want to show here is first real application. So how mild drug transformed into a very nice physical device that actually transforms the whole audio industry as we know it now. Later, by the way, the whole idea was used for barium titanate. I think it's the most prominent example of ferroelectrics, the most well-known. It was studied in USSR, in USA, in Japan, and basically it was used as a transducer to hunt German U-boats, especially in the US. Okay, and everything seemed to be fine. But later, in '72, it was very nice paper from guys from IBM. And basically they wrote the following thing. They used some analytical calculations to estimate critical sequence of ferroelectrics, below which ferroelectricity will be suppressed. And this estimation is actually for TGS, for triglycerin sulfate, is 400 nanometers. And basically it's huge. So a lot of people read this article and wow, ferroelectrics are useless. We can scale them down to use in electronics. And this 70s is like a dawn of computing edge. All this CPUs, memory, all this stuff come into play. And actually there were some works at this time about ferroelectric memory already. It's like hard to point out exact papers, exact researches, but somehow, while a lot of people lost interest in ferroelectrics, some people continue work on them. On, for example, on theoretical aspects, on soft mode, on order parameter. Some groups work on related materials, like not ferroelectrics, but for example, relaxers, different ferroic materials, multiferroics, for example. And
This is not the case. Because
What do you
I
mean?
mean, now ferroelectricity exists even in
Yes, yes. It just well, one slide away, basically, yes.
Is it all because the instability is because of thermal fluctuations, right?
Yes. So there is maybe like this, yeah.
So it is like
Huh?
easy mode. So if in the low energy, for example, when it is somewhat unstable, you cannot have either ferromagnetism or antiferromagnetism for when the iron check.
But that is different. That is different because then it is unstable to quantum fluctuations, right? And in this case, it's because of
So yes.
It different for some of that medical.
no. Okay.
So somehow Ferroelectrics survived, and I also gathered some more like computing applications of Ferroelectrics today. First of all, it's memory storage. It's a very nice commercial application. It exists. People buy this memory. By the way, it even outperforms traditional flash memory. But still, it lacks of density, and still, it's too expensive sometimes. I already told about barium titanide, about actuators, but today ferroelectrics are used in biomedical applications. Very prominent applications include looking for terahertz dynamics in ferroelectrics because people suggest that domain walls can move with like terahertz frequency, and ferroelectrics can play a role of detectors or generators of terahertz radiation. Also, for example, coupled with semiconductors, they can play a role of like photo elements. They can simultaneously register and like learn some images. And okay, I think everyone knows about AI boom, about all these chats, the different types of chats. And of course, people in the industry complain like, okay, modern semiconductor computers are too slow to teach all this model, all these neural models. And there's a lot of hype actually about neuromorphic devices. Here it's not a ferroelectric device, it's actually a memristor crossbar. But I will show you some interesting stuff about ferroelectrics that can play a role of memristors, but not on the base of resistivity, on the base of charges. So yeah, you're absolutely right. I mean, just recent decades, it's not somehow, it's not I gathered, you know, these papers specifically. It's really last decade where people studied very different textures of polarization in very different geometries of ferroelectrics. So superlattices, nanorods, nanoparticles, nanodots, very different stuff. And they found a lot of very complex polar textures in these objects. Of course, we should say thank you to modern experimental methods, especially this STEM and 4D STEM techniques that allows you to study really materials on atomic resolution. Also to synthesis techniques, of course, because, for example, at some point, barium titanide was a revolution when they synthesized ceramics of barium titanide.
Wait, what do you mean by STEM? Scanning, transmission, electron
Yes.
microscopy?
Yes.
But does it map not spin but ferroelectric model?
No, okay, I will make a comment here. So basically, you fill some lattice, and you have virtual undistorted lattice. You put one onto another and calculate polarization based on displacement of ions.
Okay.
Okay. It's yeah, it's very simple. So it doesn't measure polarization. Okay. Yes. So and experiments are amazing, truly amazing. They're really difficult. They're really interesting. But really, theoretical understanding of these polar textures is what we lack here. So first of all, I should say that a lot of theoretical understanding about ferroelectric textures comes from magnetism. So people saw these arrows of polarization, and they said, hey, it looks like in magnetism actually. We can took all the stuff, all the terms, and transfer it to ferroelectrics. But it's actually not not good. There is a mistake. It's so-called real space approach. And what is important, in magnetism, there is a constraint of order parameter to be constant. While in ferroelectrics, the main constraint is divergence of polarization to be equal to 0. Because in ferroelectrics, long-range electrostatic forces, depolarization electric fields, they play a crucial role. Consider this example. You have some, you have some slab of ferroelectric material, let's say thin film. It's uniformly polarized, up and down, doesn't matter. At the termination of polarization at the surface, there are huge bound charges. They create depolarization field and it destabilizes ferroelectricity. To avoid this energetically unfavorable configuration, ferroelectric forms domain to get rid of these bound charges, this domain structure. It looks like more like Kittel domains, but actually in ferroelectrics there are special terms, so-called soft domains, because you have also rotation of vector polarization near the surface, additional rotation. And if you look at the modern methods of studying ferroelectric materials, more theoretical methods, we now talk about theoretical methods. So, of course, you can employ analytical calculations. There are different types of atomistic calculations. Of course, ab initio, like first principle studies. Also, so-called second principle studies, for example, molecular dynamics. And macroscale methods, basically it's a solution of numerical solution of partial differential equations, but in the literature you will find this term phase field. It's called like this. I will explain a little bit later. And what we try to employ, what we try to develop here is a different macro analytical approach, topological approach. And actually here we take inspiration from the works of Heinz Hope, who actually pioneered this field of this branch of topological hydrodynamics, and works of Kate Moffat and Vladimir Arnaud. By the way, I highly recommend to read all the Arnaud books. They're really entertaining. It's truly amazing. Not only scientific ones, there's a lot of different stuff. Yes, and what is interesting, in this topological hydrodynamics, there is same principal constraint. Divergence of incompressible fluid flow is also equals to 0. So the same as for us.
Where does it come from in the case of, in your case, divergence of P equals 0?
So basically, minus the
charge.
But minus the divergence of P is bound charge.
Yes.
Yes. Bound charges, they have huge energy binding. They have like basically they destroy this configuration very quickly.
So this constraint is for the bulk, but
Sorry?
this constraint is for the bulk, but in the edge it is quite different.
No, but basically it's you see it's a global topological constraint. So it means that, for example, on the surface, the vector should be tangential to the surface. Vector of polarization. But we also come to this explain. Okay, let me.
So which means that the situation you can see the situation not like in the middle panel, like thin film.
This one.
No, upper. Yeah.
Yes. No, you can see such situation if you apply very strong electrical field, for example, polarized to cell.
Yeah, but in this case, you don't have divergence of P equals to 0.
Yeah, of course. It's like, okay, I will come to this a little bit later because I also managed this. Okay. let's go further. So I will explain our approaches to research. So first of all, this big scale topological approach. It consists of three key ideas. First one is that we use just topological approach. Basically, it's homotopy theory. We have two spaces, basically two manifolds. One is coordinate manifold. It's something embedded in n-dimensional Euclidean space, so Rn. And one manifold is for order parameter. So its configurations that polarization can take inside the material. Next big idea is using of streamlines instead of vectors. Because actually I show you some experiments, and all the people use these arrows to represent polarization. And you will see scenarios when this representation hides from you crucial details of how polarization behaves in ferroelectric. And finally, it's similarity between how polarization behaves and how incompressible fluid flow behaves. Again, it's topological hydrodynamics. So next crucial component is Ginsburg-Landau function, Ginsburg-Landau theory. Basically, Landau pioneered theory of phase transitions. And it's interesting to note that Ginsburg applied this Landau theory to ferroelectrics even before it was applied to superconductivity. So basically, it was one of the first applications of Landau theory of phase transitions to some materials. Okay, so in our case, Ginsburg-Landau free energy looks like this. We have four components. Ginsburg-Landau energy itself, which gives you spontaneous polarization, rise for spontaneous polarization. Gradient term, which finalizes non-uniformities, but basically gradient term gives you a different kind of, for example, domain walls. And electrostatic and elastic terms. Electrostatic term can give, for example, possibility to apply electrical fields. Also, of course, it's connected with this divergence of P. If you have some bulk charges inside of volume, you will get sources, since you will get some kind of destroy of your spontaneous polarization. Elastic energy allows you, for example, for elastic coupling, if you want to simulate thin field, you can apply effect of substrate on this field. Of course, internal elasticity is also taken into account.
Sorry, but this
Yes.
phi here is.
So phi. Sorry. So P is spontaneous polarization, is order parameter actually. Alpha is A is Ginsburg-Landau coefficients. G here is gradient coefficients. So here phi is electrostatic potential. And delta is free charge spinning length. So U is tensor of elastic deformations, and CQ is different tensor. So C it's actually coefficients for linear elasticity. Q is electrostrictive coefficients, tensor of electrostrictive coefficients. Yes, and of course we actually get our real equations from these relaxational equations. So basically, it's first variation of this functional. And these equations are enclosed with elasticity equation and Poisson equation to find out what elastic strengths are, what electrostatic potential are for given distribution of polarization. Okay, and our main numerical tool is finite element modeling. I already said that in literature people use this phase field term, but it's really funny sometimes people say like, we employed phase field model, we solved this equation. And you just wonder how you solve it, because you don't provide any information. Is it finite differences, finite elements, finite volumes, some spectral elements? A lot of ways to solve equations numerically actually. So here we employ finite element modeling. It's a pretty versatile method that allows you to work with complex geometries and also it has some nice numerical properties. Let's quickly consider the case of Poisson equation. So equation itself and Dirichlet boundary condition give you so-called strong form of equation. Then if you take integral over the domain, the solution domain, and multiply it by some arbitrary function, you will get so-called weak or variational form. Here you can see this example of nice numerical properties. Through integration by parts, you can reduce order of derivatives. It really helps a numerical solution. It makes solution sometimes faster, sometimes more stable. And last step is to transform this weak form into a continuous set of finite functions. Basically, you can represent any function as sum of known functions multiplied by known coefficients. Then you need to form a linear system and solve it. In case of Gisbert-Leonard equation, of course, it will be a non-linear system, but again, principle is pretty the same.
But if non-linear, then equations for this CA will be also non-linear, so it's not like variational.
You need to employ just different, for example, Newton method here to solve some. Yeah, yes, of course. I mean, the idea is pretty the same. Okay. Now we can talk about our results finally. So we start with nanoparticles. I already told that there are a lot of different research on very different geometries of ferroelectrics, but it's interesting that very few of them on about nanoparticles. Here are two prominent examples. One experiment on pretty big barium titanide nanoparticle, where vortex state was identified, and one very recent actually on smaller nanoparticles, about 10 nanometers in diameter, when also vortex state was identified by authors. But thanks to open data, we reconstructed the behavior of polarization lines in this nanoparticle, and we acquired much more complex things than just vortex. And it were one of our main results as from Hopfield. So first of all, let's see how we can achieve such state, this Hopfield state. Let's start with some spherical ferroelectric nanoparticle and consider it has uniform polarization. As I already told you, it's bad state because polarization lines, they abrupt on the surface, they create bound charges, and it's not this state is not energetically favorable. Okay, so to get rid of these bound charges, we need to get to divergenceless state. Obvious configuration is just vortex, and actually it's a stable configuration because you see lines of polarization line in vortex, they are tangential to the surface of nanoparticle. And actually it's stable state near the temperature phase transition. But there is one problem. Problem is here you have singularity in the very middle, in the center, in the core of vortex, yes? And system, ferroelectric system, tries to be as uniform as possible. So polarization vector should be very uniform. Okay, we can get rid of this state too. Let's put some polarization at the core of the vortex as helix.
What is this term that prevents singularities? Is it the
Is gradient term actually?
Gradient
term. So sometimes it's connected with elasticity, but mostly gradient. Yeah, okay. It prefers polarization to be uniform. So, okay, yeah, and we can put polarization at the very center of vortex, like helix, but again, we get these bound charges on the surface. And there is only one step to follow.
This solution of the equation you showed before?
Just one moment. These and these are solutions. These not. It's model case. Now I will show solutions next. The real solutions. It's just a model case to see how this thing happens. So yeah, and basically what you need to do is allow this helix line to flow back along the surface of nanoparticle. keeping tangential to it, and wow. And you will get it's okay, yeah? Okay, and you will get this copion thing. So what is copion? It's a version 3 configuration of polar field, and it's actually unique topological state. Let's study it more thoroughly. So
chaotic?
Huh?
Is it chaotic?
no. It's well said. It's not chaotic at all. I will show you chaotic configurations also later. I have everything. Okay, so let's see. Sorry, yes. Okay, here you can see different types of lines that constitute hope field. So basically, all these lines, they are closed loops. They are tangential to the surface of nanoparticle. They have no self-intersection. They are all tangled, and they form dense subset inside the volume of nanoparticle. Basically, this non-trivial linking of streamlines is a topological characteristic of such object. So let's go one by one and see different characteristics of Hopion. First of all, consider distribution of PZ component of polarization. We can see that it goes up at the core of Hopion and it goes down at the periphery. As I already told you, it's very uniform state except two singularities at poles, and also this state possesses chirality. We will discuss chirality in more details later, but basically it's asymmetry of object to its mirror reflection. And chirality, as you can see, is also concentrated on the poles mostly. One of the most prominent results here, you can see distribution of vector field on the surface of this nanoparticle. And here, what we see here is implementation of Poincaré-Hopf theorem. So the theorem states that if you have some smooth manifold, vector field, also smooth vector field defined in this manifold, and some finite number of singular points, then sum of indices of the singular points will be equal to Euler characteristic of manifold. For S2 sphere, the Euler characteristic is 2, and actually we have exactly two singularities with value of with index of 1. So in sum, the gear is 1. For example, if we consider torus, for torus, Euler characteristic is 0, and on the surface of torus, you can create tangential vector field at every point. And here is prominent example of so-called hairy ball theorem, because here you can't create on the sphere vector field that is tangential on every point of sphere.
What this was spherical. What the spherical particle, how the positions of these poles are defined, which condition?
It depends on the symmetry of crystal. For example, in this case, they're aligned along one direction because of PZT. It's PZT crystal. I will also go for details later. So yes, and these poles align with one direction, but you could create some, for example, model functional, and it will be directed, for example, aligned with the axis.
By the way, is this state gives the minimal energy at every radius of your particle, or it is not?
I also have something about this. It's a very interesting question, but yeah, it's very stable state. It's actually a stable solution with minimum of energy. Yes.
What's the difference between the Poincaré-Hopf theorem and the Gauss-Born?
Sorry, Hitchcock theory. At some point, you can consider it some kind of some special case.
So how do you calculate the index? So for Gauss-Born, you can do
No, singular points have well-defined indices. So, for example, these singularities are just one, dependent on the rotation of vector field. Plus one or minus, it can be also minus one.
That's a problem. So how do you define the singularity? So numerically.
Okay, numerically they are defined as basically as equivalence of vector field. Okay, I will have like really more examples, but basically it's just equivalent of vector field. It will give you sign and value.
Well, if you calculate it with Gauss-Bonnet theorem, and you can just do the integral, and this will give you some finite value.
No. I mean, for calculated field, for experimental field, for modeled field, you can you have all numerical data, so you can calculate. Yeah, it's pretty easy actually.
So the index.
In this case, we just know the index for this stuff. We don't need to calculate it, but yeah, for different cases, of course, yeah, you can compute it. No problem. Okay. Let's dive into some details. So I already told you about drawbacks of this real space approach. And here you can see two pictures where vector field on the surface of nanoparticle is presented, yeah, and on the cut of this nanoparticle. I guess you can't say that it's some kind of non-trivial configuration of vector field, looking only on the errors. But streamlines immediately give you very nice Hopfion. Also, you asked about like position of these singular points. Here you can see very interesting stuff. Polarization lines, they're not straight. They're actually deformed by crystal anisotropy. And this anisotropy also defines position of different singular points. Yes, and of course we calculated bound charge and electrical field for this configuration, and they're vanishingly small. So this dB equals 0, is confirmed.
So the point about streamlines is that they're useful for visualization of non-trivial.
Okay, first of all, for visualization, because you can immediately get the picture of what happens here. You can immediately distinguish between vortex, Hopfion, maybe some other space. But also, for example, with these lines, you can study linking of these lines. So you can calculate linking number if it somehow you need it. So yes, and this just vectors approach, unfortunately, it's hard.
Because with streamlines, how are they defined?
Okay.
Because vectors for every unit cell, you can put vector in the direction of polarization in this unit cell. Yeah. But
so basically, it also comes from hydrodynamics. It's a very simple differential equation like dx by v. You have vector v. You have vx, vy, vz, and by dx by
velocity.
You start at one
it
point,
can be velocity, but it can be polarization. So it's any vector field actually. You can draw this way in a vector field. So dx by vx equals dy by vi equals dz by dz, and it equals some dt. T is parameterization parameter. It can be, for example, time. It can be, I don't know, for example, arc length or some segment. It's different stuff. You can parameterize it actually differently, but yeah. So it's basically a simple differential equation.
For hydrodynamics, it's literally a path of the particle which starts at some point and then follows the vector field, kind of, right?
Yes. It's actually it's the same here, but we have like frozen configuration. We don't have this, dynamic flow.
So it's like continuity equation, like 0 over d2. So the divergence over time equals plus divergence over current equals 0.
No, it's not the same. No.
No, you just write a tangential equation for tangential to the vector field at each point. And this dt is actually length along the streamline.
Okay.
Yeah, but basically it's configuration of this vectors are tangential, so lines
It's
is
easier.
vectors tangential.
Easier.
Yeah, it's easy. It's just geometry.
Okay, so you already asked a question about size of particles. So we plotted phase diagram, temperature and temperature values of nanoparticles. As you can see, Hopfion occupies a significant part of this phase diagram. I already told you that vortex is also a stable state near the temperature of phase transition. And for particles smaller than around 3 nanometers, we have paraelectric state. Okay, also,
And temperature only appears in the equation in the Landau.
in alpha 1, yes, it's the temperature only in the Ginzburg-Landau term of this Landau free energy. Yeah. Okay, also we have some polarization characteristics for specific nanoparticles. It's interesting to note here that people often use this thing. T is vorticity. It's like just rotor of P, and they use it as some kind of numerical evaluator for different complex topological states. But please note that you see this vorticity, it turns to 0 with polarization. So basically, when you get to paraelectric state, you get both square magnitude of polarization get to 0 and vorticity get to 0. But what is interesting, chirality indicator, it vanishes before the phase transition. It vanishes when Hopf transforms to vortex. So it's pretty good to keep in mind if you analyze such systems. So there are very different indicators, and vorticity is like bad indicator if you want to distinguish some complex transitions.
And how this chirality is defined?
Chirality, I defined it already. It's P dot rotor P.
Susceptibility.
Is it some general definition for any vector field?
It's nice question. It's actually it's more local. Because it's like numerical evaluation of this chirality, but actually there are more complex.
In case of electromagnetic field, there is a measure of chirality, also called chirality, but it looks different.
Yeah, it's a little bit different because okay, but Ferroelectric field is the same. It's as I told you, it's just asymmetry to the mirror reflection of the object.
Yeah, but you have to introduce the measure of this, and there are different ways to do this. So this is, I see, I haven't seen this expression earlier, but in case of there is a measure of chirality of electromagnetic field. I know it involves two vectors E and H. In some like cross product and dot product of the three of them. It looks different. So I'm asking, where did you take this measure from? Is it some
okay? It's some
general accepted?
It's some general accepted. It's not like no exact, but it's widely spread to just distinguish between different non-symmetrical states where you have some achirality. So basically, non-zero values of this gives you indicators that this state is chiral.
This is local. It depends on point. P depends on point, right?
It's P at.
But that means chi depends on point.
Then you integrate it probably.
So basically, this one is just sorry. This is like a density of this value. But yes, of course, you can calculate average chirality over the volume as an integral.
Okay, you can change sign. So when you integrate, you get zero. But
sure. I have such cases. Yeah, I have such cases. Sure, I will show you this.
Like a borrowed concept from the Berry curvature.
No.
No.
Okay, and before going to the topological phase transitions, we also discussed the topological stability of this Hopf. Here I should mention Kolmogorov-Arnaud-Moser theorem. Basically, this theorem is generalized to static divergence-free vector fields, and it states that Tori winding of field lines remains intact under small adiabatic perturbations of free energy function. Here we introduce, for example, first of all, size of particles. I have shown you that up to some values Hopf exists. But if you go to very big particles, for example, here you can see this particle with a radius of 100 nanometer, then the state of lines looks very different. Actually, it's some kind of transformation from order to chaos. in this case, lines, they tend to pass at very different places of this particle, and one line tend to feel like the whole volume of the particle. Also, we estimated stability of hopium, for example, against free charge carriers. So it introduces the electrostatic equation, and you can see that with some, for example, low concentration, less than in semiconductors, for example, some lines start to abrupt in the surface. So, but still in the volume you have presence of torus. And with some high concentrations, something like with semiconductor, maybe a little bit higher, of free charge carriers, you get the whole state destroyed. You see all the lines now abrupt on the surface, and you have no signs of torus inside this nanoparticle now.
Have you tried computing the Lyapunov exponents for this trajectory?
No, you mean chaotic, these diagrams? No.
Rigorously prove that it's chaotic.
Okay. You see, it tends to be chaotic. It's just like transition. It doesn't mean that it become fully chaotic. Also, it's connected, with ergodicity. But no, it's basically it's a good idea. Actually, it's something that maybe we should take into account and try, because there are different stuff called relaxers, and there should be chaotic behavior, and actually it's a good idea to confirm it like numerically. Okay. Yes, and I told you that I will tell you something about applications of this stuff. So here we consider the nanocomposites of such particles. So, for example, we have two nanoparticles, but we have periodic boundary conditions, so we can put like 3 of them, 4 of them, more. And two nanoparticles touch each other with different size of spots. So, for example, here is small spot, here is bigger spot, here is actual values. What is interesting we see here is even with a small spot, we have polarization leakage from one particle to another. But volumetric torus, they still persist. And with bigger size of this spot, we have pretty different behavior. We have strong coupling between these particles, and actually basically no torus between them. And what is interesting, if you build a device that's presented here, so basically if we try to take a couple of particles and confine them between electrodes, we have get very nice hysteresis loops. For example, for when particles have no contact, you have this straight line. Okay, it's obvious. But more and more contact they have, more and more jump states you have on this hysteresis loop. And actually, it's a good candidate for different neuromorphic applications where you need to distinguish between a number of different states in the object.
Are the terms weak and strong coupling used here in the conventional sense?
It's like more also terminology. Sorry. Yes. Not super rigorous, just to take into account this spot and how lines goes from one sphere to another. Okay, and finally, yes, topological phase transitions that happens in these nanoparticles. But I think it's better to can you escape and
Yes.
open the video? Yes, it's okay.
No, it's on the desktop.
Desktop. Okay.
Oh, you can find desktop again.
Yes, and sorry, I can.
Right up corner. Yeah.
Oh yeah, wonderful. So let me just. So what you can see here is actually this ferroelectric nanoparticle between two electrodes, And now strong positive electric field is applied. So it's polarized like more or less uniformly, but you see that lines actually have helical structure. And what we do now, we go from positive fields to zero and then to negative fields. Let's see what happens with the structure. So first of all, you can see condensation of torus line in the center of nanoparticle. Peripheral line also condenses, but not so fast. At some point, you will see that lines lose connection with electrodes, right now and now.
Real type evolution, or you are changing the strength of
It's like yeah, let's say real time. The only thing, just let me, I will answer your question.
Is it a bucket process or what about time?
You saw relaxation equation, and there is gamma parameter. And in our simulations, we take it to be equal to unity because it's like fictitious time. We don't know exact time. Like, for example, I have, let's say, 100 time units. But I can tell you exactly, is it, for example, 100 nanoseconds or less or more? But for us, it doesn't matter in this case because the evolution is...
For you, it maybe, but in a real experiment, it should matter.
Yeah, of course, if you do this with real experiment, I will calculate time figures.
Okay.
If there's some relation between the periodicity of the inner polarization line and the outer polarization.
It's a really interesting question. I haven't thought about it, but I think somehow through, for example, Hopf invariance, there may be relay. So maybe there is some a relation between the periods, but I don't know, unfortunately.
What about the radius of this nanoparticle? If you decrease the radius of nanoparticle, maybe you can just observe when polarization happens.
Yes, of course, a smaller nanoparticles field will introduce the states faster, will affect the states faster. Yeah, so just at some point, the whole particle becomes partitioned into toric. And upon going to negative electrical fields, you can see that we form two helical lines. Again, they got distorted. And actually, it stayed symmetrical to the initial one, but the polarization looks not upward, but downward.
And it's periodic. Periodically switching the non-polarization from up to down.
Yeah, there's definitely some periodicity. It's we need to think about it. So how to make full screen? Okay. Can I? Okay. So okay. So here, these figures, some without dynamic static cases depicted. Actually, it's Poincare cross-section, called Poincare cross-sections of these lines. And you can see that the whole system is structured. It's divided into toroidal cells and cylindrical, like vortex cells. And it's very interesting because actually it happens according to.
Sorry, could you explain?
Yes.
Like, what are the colors and
colors just to differentiate between different structures. For example, here blue lines are helices, not towards like cylindrical cells, and here green one is open torus. Here, for example, red lines are helices, and green and yellow they are toric. It's just to differentiate between them because if I put them in one color, it would be hard to spot. Yeah.
So how do you define this shape by numerical calculate each?
You see actually by this streamline. So you see if it's closed or not.
But you need to calculate some property of the streamline to define this shape, right?
Yes, you can, but you can do it just by eye.
By eye.
Yeah, you can just see it.
Wait, one cross section is in this case literal cross section, right? Or
It's more or less because it's like half of particle because there is another half at the back, and true concave section should be just two-dimensional, of course, but it's also for like visualization purpose. Now it's more this you can see more details. Yes, and what is interesting, all this partitioning of ferroelectric particle is goes in full agreement with Arnold's theorem. So I will not read the whole theorem. Basically, it states that if you have some volume, and inside this volume you have divergence free incompressible fluid, the space will be partitioned into toroidal or cylindrical flows. And basically, that's what we see in our case, in full agreement with Arnold's theorem. Our nanoparticle also partitioned into tori or vortices, which are cylindrical cells.
and they are not overlapping at all. Or how?
No, they are not overlapped. They have distinct boundaries, and actually, they're also separated by Bloch points. Okay, so that's all about nanoparticles. We now talk about chirality. I already told you that chirality is some asymmetry between object and its mirror reflection. So hence we all know the chiral, yes? Because you can't superimpose your right hand with its mirror reflection. But in nature, there are a lot of chiral objects. Someone says that even universe is chiral. I don't know exactly. So you can see like sea snails, DNA molecules. Also some abstract objects, geometric objects can be chiral or achiral. And also artificially created objects also can be chiral. For example, different nanoparticles. But what is very interesting, you can switch chirality in any of these objects. So chirality is somehow built in this object, it's encoded inside, yes? And what we show here is you can switch chirality in very different ways in ferroelectrics. Here we consider, again, our nanoparticles. So basically, it's what we just saw. It's, again, hysteresis loop. We go through electric field, but now we measure not polarization by chirality. Now, yes, please note it's volumetric value, so as told, it's integral value over the volume of nanoparticle, but colors encode chirality at point. Okay, so and actually, what we see here, first of all, you see that chirality is unbalanced. Some of parts of the nanoparticle contribute more to chirality than other parts. For example, it's easy to see that core contributes more than periphery. But, for example, if this core is negative, periphery still can give a pretty big positive value. And its case, for example, for this state 3, you see it's 0, yes, because part of core is negative, part of core is positive, and they compensate it. Yes, and what's interesting, going through this switching this nanoparticle with electrical field, you can really switch chirality from left to right. And what is interesting, you can distinguish the states, for example, with polarized light. Left to right, polarized light. So here we can see switching before two different states. But what's interesting, in nanodots, we found the possibility of switching between 4 different chiral states. Because chirality, based on this description, cannot be only left and right, but also plus and minus. Actually, you can use just rules of your hands and see the direction of rotation vector with 4 fingers and with some directional vector in the center. So again, here's experimental setup. The ferroelectric nanodot is confined between two electrodes. There is some space. It may be vacuum or some dielectric. And here we see the chirality switching protocol for such nanodot. First of all, again, what is interesting, if you look at hysteresis loop, it looks absolutely trivial. So nothing special about this behavior. It's like normal hysteresis loop. Maybe it's a little bit narrow, but doesn't matter. While chirality possesses very interesting and complex behavior. What is especially interesting, taking any state, you can come to any other state. Here, the chirality depicted from the bottom of nanoparticle, sorry, nanodot, because from the top it always looks like a fontaine distribution, and here chirality is concentrated near the center again. Yes, and going through this electric switching protocol, you can achieve any of these states, and all the states are distinguishable. One note to make here, so if left and right chirality can be distinguished by light, for example, then up and down direction of polarization, of course, you need some other technique, for example, PFM, piezo force microscopy, but again, for such case, it can be fairly simple setup. Okay, so now
Yeah, I waited for experiment.
okay, now we talk about also interesting topological stuff. I told you about ferroelectrics, but ferroelectrics can be a little bit different. They can be multi-axial and uniaxial. Uniaxial ferroelectrics is a special type of ferroelectric where spontaneous polarization can look only up or down, so only two directions are possible. If you remember all this divergence P stuff about bound charge, then in this uniaxial ferroelectrics, only two types of domain walls are possible. So head-to-head, where vectors meet, and tail-to-tail, where vectors diverge. And it's like natural to expect that these domain walls will be charged. And actually, that's the case. For example, lithium niobate, very famous uniaxial ferroelectric, has a very strong charge on the walls inside the material. Very interesting case of lead germanite. So people studied this thing, and they found no signs of conductivity. So here you can see conductive IFM near the head-to-head domain wall, and no signs of charges. It's measured with Kelvin probe force microscopy. So again, near the same domain wall. It's pretty curious behavior actually, and we employed some modeling to explain this. So we modeled a big chunk of this material. Actually, we can see that results of modeling minus the experiment, overall structure of domains looks the same. And what is interesting, bound charge near the domain walls is indeed very small. But how to explain it? It can be explained actually in one way. So if you have some rho-z component of charge, so the charge that comes from head-to-head or tail-to-tail configurations of polarization, so it can be compensated by lateral components. So some xy, some polarization should be in xy plane. And then total bound charge, which constitutes rho-z and rho-xy, is indeed small. And this in turn suggests that we have divergence-free configuration of polarization field in this case. And actually, it's in a full agreement with topological hydrodynamics theory. So here you can see polarization lines of this field. To explain this behavior, we can draw a simple analogy. Consider two flows of water that should encounter each other. Yes, to avoid shock formation, they just split in V-shaped configuration. Actually, through our particle, we called it scissoring, so V-shaped scissoring, to avoid shock formation. So here we study some topological properties of this configuration. First of all, it's elementary piece of this bifurcating structure. You can see two V-shaped flows of polarization, and they don't meet each other here to avoid formation of bound charges. We plotted the surface of domain wall in this case. It's pretty interesting that it is a singly connected surface that spans through the whole volume of crystal, and it contains a lot of V-shaped structures inside this domain wall. So basically, it's singular saddle points, and you can describe them in two ways. First way is using language of differential geometry. It's actually your question about how do you calculate singular points. So you can calculate index of singular point using Jacobian of vector field. But you have another description. You have use, yes, and based on the configuration, if it's head-to-head or tail-to-tail, you have +1 or -1 index of this saddle point. But also you can use this integral. Here you integrate the normalized vector of polarization over small surface that surrounds this saddle point. And values of this integral are exactly the same as values of equivalence. So it's +1 or -1. Actually, this duality of description is formally called Poincare duality. And exactly this connection between differential and topological properties, they give you so-called topological stability or topological protection. So this point is topologically stable. And yeah, you asked about experiments. So maybe it's all model. It's all not true, yes? So our colleagues made so-called TPFM experiment inside crystal. TPFM is a tomographical piezo force microscopy. It consists of mechanical removing of layers of material with tip of microscope and simultaneous piezo force microscopy scan. Upon removing the material, you get a series of scans, and using simple calculations, you can actually produce the three-dimensional structure of the domain wall in the volume of material. And what they found out, the structure of domain wall in this crystal is really a singly connected surface, and it's full of these saddle points.
But doesn't mechanically removing parts of material renormalize the whole structure?
Good question. I haven't mentioned it, but it's first of all, it's bulk crystal. It's not thin film, and bulk crystals are really more resistant to such things. But again, it's like something handmade manner. They have like more rigorous statistical tools. So upon each scan and upon each layer removing, they gather some statistics of domain wall widths, of domain wall frequency distribution, and using the statistical tools, they confirm that removing of the material doesn't affect the internal structure of domain wall. So maybe it moves like, plus minus nanometer, but you can see scales at micrometers, so it's huge actually. Also, there was complementary experiment, not on PGO, but on TGS, it's trilithium sulfate, and they discovered exactly the same structure of domain wall. We decided to make like a full theory for all the uniaxial ferroelectrics, because actually I already mentioned that in lithium niobate you have charged domain walls. And for example, in erbium manganate, you have charged domain walls, but with some saddles. But now the structure is disconnected, so it's not singly connected surface. And we introduced, again, free charge carriers inside the volume of material. And depending on the concentration of free charge carriers, we get non-charged domain wall that is singly connected all over the volume of material. Low domain wall with low charges, but with some, again, disturbance, with some tears. And finally, we get very strongly charged domain walls for big concentration, large concentration of free charge carriers, which is actually a non-singly connected surface. Okay, so the last one is, do you have some time?
Well, maybe for a couple of slides.
Okay, I will quickly introduce now application because it's pretty interesting. All this neuromorphic stuff. Basically, the main idea of going from phone name and architectures is to unite compute and storage operations. So your elements simultaneously can compute something and store some information. And here is interesting case of PZTs in films. So upon repolarization of these films, the surface of film is traced with conductivity traces. And conductivity is pretty good. Actually, it's nanoamperes. So we modeled also this case to know how this, why this conductivity happens, and found out that actually in these PZT thin films forms very complex network structure of domains, of interconnected domains. And because of elasticity compatibility conditions, because of large deformations of this film, all domain walls, including 190 domain walls, they're inclined and they're all charged, and they attract free charge carriers. These bound charges walls attract free charge carriers from the volume of the material. So basically, we modeled full three-dimensional case, which shows that high conductivity traces, they follow the places where different types of domain walls are interconnected. And basically what experimenters show here, so if you read conductivity somewhere in the center of material, and upon creating some repolarized spots, you get higher and higher and higher conductivity. Upon reverse repolarization, you have lower, lower, and lower conductivity. And basically, this is pretty interesting from application point of view, because such kind of ferroelectric can be used instead of memristor in this cross paths with different reprogrammable conductivity levels. So, okay, I have some general conclusions. I will not read them. And just, it's like shameless self-endorsement. We did a very nice review on topology in ferroelectrics. It's published in Physics Records recently. I highly recommend reading it. It's pretty enjoyable, and a lot of people say that you have very nice illustrations. So,
Yeah, let's.
thank you very much for your attention.
Okay, so we have some time for questions. Probably we can start with Zoom audience.
I don't know. Something. No?
Okay, I wanted to ask about the boundary conditions. So in all these simulations, they are very important probably. And is it just Maxwell boundary conditions, or there is something specific about them?
So indeed, in different simulations, you have different boundary conditions. Just for example, here to simulate these clashing domains, we have antiperiodic boundary conditions for polarization. Or for example, in case of, let's go, these PZT thin films, we have just boundary condition, just simple Dirichlet boundary condition for electrostatic potential and periodic boundary condition on the sides to create really big thin film. In case of nanoparticles, for example, something like this, so you have pre-boundary condition on the surface of nanoparticle because it's embedded in some medium, and top and bottom of medium you have again, Dirichlet boundary condition for potential to simulate application of electrical field. So basically, very different boundary conditions depending on the scenario, depending on what we're doing.
Right. So the solution is always a single one, or you have some, variety of degenerate solutions.
Yeah, I see what you mean. It's actually a very important question. We utilize different methods to ensure that we have some stable global minimum solution. Because sometimes you can get a lot of metastable states, again, depending on what you simulate or how you simulate. So we employ a lot of like physical things like shaking all the system, a lot of numerical things like moving the grid a little bit, to ensure that we push the system out of some local minimums.
Thank you.
Okay, question. Does anybody try to reproduce or confirm existence of this Hopfield state?
Okay, that's a nice question. Actually, in some sense, they are found. Not in particles, in superlattices. Actually, it's very universal structure. It can exist in superlattices of what? In superlattices of PTO, STO, Lie-type night, social night.
Not nanoparticles.
So nanoparticles, yes. But okay, I will just tell you, it's maybe a little bit like of overview of our future, so it's a real solution. You will get Hopfield in nanoparticles. We studied some experiments, we did some interesting stuff, and for example, in small nanoparticles, there are charges or fields that destroys this state, but you can see like signs of this Hopfield state was there. But basically,
how do they create this state? Because you need, if you apply, for example, homogeneous electric field, one can assume that polarization also will be homogeneous. So how to create this?
If you have ferroelectric nanoparticle, it's, I don't know, hangs somewhere in vacuum, yes? You know,
no, it's this experiment. So you have
no, it's this
experiment. You put some sphere or nanoparticle is there and apply voltage. You obtain
you will apply you will get uniform state, but uniform state you will get only with very strong electrical field. Normally you will get these helical-like states.
But what is the criteria how to detect it? Because hysteresis is not enough, right? To say.
It's so first of all, you can utilize, for example, chirality. You can measure it by light, and if you see some signs of chirality, then it's definitely not vortex. Most likely, it's Hopfield. Of course, I showed you this. Sorry, I didn't mention too much information because actually this very nice experiment is for this stem on small nanoparticles, and these people they did like polarization mapping over the whole volume of nanoparticle. But they reconstructed it not very properly. And we did the reconstruction of lines, and actually it has signs of Hopfield. But it's not Hopfield because it lies, on some grids that attract some charges. If you somehow can lift this particle, you will get Hopfield. Because it's also something that very important that I show that it has topological stability. You can get smaller or bigger nanoparticles. You can introduce free charges. You can introduce bound charges. You can introduce electrical fields. You can introduce some elastic deformations. And with some values, this state resists, but somehow gets deformed. With some big values of these perturbations, of course, this Hopfield state is destroyed.
I also wanted to ask about the stability to perturbation because you showed the results for spheres, but the real nanoparticles are strongly deformed. I can understand that the topological states will be stable somewhat, but the chaotic states will probably be even preferential if you add some symmetry, because we know that from the theory of billiards.
Okay, good. So for bigger nanoparticles, of course, I think for bigger nanoparticles, very non-uniform action, yes, and it plays role. For smaller nanoparticles, actually we show through a lot of calculations that some kind, of okay, not holes, but some kind of deformation, so more material, less material, the state still persists. Sometimes gets something very funny, like for example, two hopefields inside, not like single ones goes from the center to the periphery, but two align with each other. So yes, some metastable states maybe, but again, when the particle is really deformed, it's really not very non-spherical.
I wonder the continuity of the chirality flow. So for the scissor flow, you actually will have a laminar flow between these two kind of propagating flow. So the velocity is
This one.
there. As the interface of the up and down, so the chirality shall also be there or not.
No. Basically, yes, there is some maybe very little discontinuity of polarization, but
It's continuity.
it's not that big to create strong enough depolarization field. So, but basically, as you can see, so real charge is not exactly zero; it's just small.
So another question is that if you consider Mobius strip and you apply the theorem to the Mobius strip, you have a tangential polarization along the Mobius surface. Does this mean that you will have a zero polarization at some point?
Look, it reminds me a joke by Arnold. So he came somewhere and said, "Consider that belief not on the ball but on the torus."
Okay.
And they were, yeah. So no, sorry, it's pretty okay. Maybe somehow you can achieve the state, but it's not like super realistic. But yeah, it's pretty interesting. That's pretty good.
I think it's easy to do the calculation for the strip.
No, something maybe with crystal anisotropy you can get such stuff here. Yes,
Thank you.
All right, if there are no more questions, then let's thank the speaker again. And we also have a small tradition to all the speakers of the seminar, and especially to new members of the team.
Thank you.
Small souvenir. All right, so
Well,
let's go.
Thank you very much.
Season финале называется.